Hello everyone, welcome back. What if I told you that a complicated circuit with several sources and resistors can sometimes be replaced by just one voltage source and one resistor? And the best part, as far as the load is concerned, the new circuit behaves exactly like the original circuit. This is the idea behind Thevenin's theorem. We already know how to solve circuits using nodal analysis, mesh analysis, and superposition. But sometimes solving the entire circuit is unnecessary. If we are interested in what happens at just one pair of terminals, Thevenin's theorem can reduce the entire network to a very simple equivalent circuit. So let's understand exactly how to do that. Before looking at the procedure, let's first see what the theorem actually says. Thevenin's theorem states that a linear two-terminal circuit can be replaced by an equivalent circuit consisting of a voltage source VTH in series with a resistor RTH, where VTH is the open circuit voltage at the terminal and RTH is the equivalent resistance seen from the terminals when the independent sources are turned off. In simple words, a complicated linear two-terminal network can be replaced by one voltage source VTH in series with one resistance RTH. That's the basic idea of Thevenin's theorem. Which part of the circuit are we replacing? Suppose this resistor is our load RL. We are interested in the voltage or current through this load. The first thing we do is remove the load. The 2 points where the load was connected become our output terminals, say A and B. The entire network on the other side of these terminals is what we want to replace by its Thevenin equivalent. Finding VTH. The first quantity we need is the Thevenin voltage. Remove the load and leave the output terminals open circuited. The voltage across these terminals is the open circuit voltage, that is VTH equal to VOC. For the circuit shown here, no current flows through the resistor R3, so VTH equal to V1 into R2 divided by R1 plus R2. In this case, we easily found VTH through voltage divider approach. But in general, we can use nodal analysis, mesh analysis, voltage division or any other convenient method to find VTH. Next, let's find RTH. For a circuit containing only independent sources, we need to remove the load, deactivate the independent sources. If we have voltage source, we need to replace it with short circuit. If we have current source, we need to replace it with open circuit. Then find the equivalent resistance looking into the output terminals. For the circuit shown here, resistor R1 and R2 are parallel while their combination is in series with R3. So we obtain this particular equation. Now that we know how to find VTH and RTH, let's see what the complete Thevenin equivalent looks like. Once we know VTH and RTH, the complicated network can be replaced with VTH in series with RTH. Now connect the load RL. The entire problem reduces to a simple series circuit. Therefore, the load current IL is given as VTH divided by RTH plus RL and the load voltage is VL equal to IL into RL. Hence, VL equal to VTH into RL divided by RTH plus RL. Now, let's apply this complete procedure to a simple circuit. Consider the circuit shown. We have V1 as 1 volt, R1 equal to R2 equal to R3 equal to RL, which is 1 kilo ohm. We want to find the load current IL. First, remove RL from terminals AB. The terminals AB are now open circuited. Next, we need to find VTH. Since terminal A is open, no current flows through resistor R3. Therefore, there is no voltage drop across R3. So the voltage across AB is the voltage across R2. Using the voltage divider rule, we get VTH equal to 0.5 volts. Next, let's find RTH. In order to do that, deactivate the independent voltage source V1. Since it's an ideal voltage source, replace it with a short circuit. Looking into the circuit from the terminals AB, R1 and R2 are in parallel. Their parallel combination is in series with R3. So RTH equal to R1 parallel to R2 plus R3. The result of this parallel combination is R1 into R2 divided by R1 plus R2. That gives us with 0.5 kilo ohm, which when added with 1 kilo ohm gives us our final RTH value, which is nothing but 1.5 kilo ohm. Reconnect the load and find IL. The original circuit can now be replaced by its Thevenin equivalent. VTH is 0.5 volt in series with RTH equal to 1.5 kilo ohm and the load RL equal to 1 kilo ohm. Therefore, IL equal to VTH divided by RTH plus RL, that is nothing but 0.2 milliamperes or 200 microamperes. This is how you can apply the Thevenin's theorem and reduce the original circuit to a simple series circuit. Now let us discuss another direct way to find RTH. Since we are using the same circuit, we already know the open circuit voltage, which is nothing but 0.5 volts. Now, instead of deactivating the source, short circuit the same output terminals AB. Applying KCL at the node and using Ohm's law, we obtain the short circuit current as 0.333 milliamperes. Therefore, RTH equal to VOC by ISC, that is voltage when AB is open circuited and current when AB is short circuited. That gives us with 1.5 kilo ohms. So we obtain the same RTH but this time directly from VOC and ISC. This method can be useful when finding VOC and ISC is easier than finding RTH by the conventional approach. The important exception, that is dependent sources. What if the circuit contains a dependent source? The method for finding VTH does not change. We still remove the load, open circuit the output terminals and find VTH, which is nothing but VOC. The difference comes when finding RTH. We cannot simply deactivate the dependent sources and use the resistor simplification method. Only independent sources are deactivated. The dependent source remains active because its value depends on voltage or current elsewhere in the circuit. So for dependent source circuits, we need another method to find RTH. Test source method. After removing the load and deactivating the independent sources, keep the dependent sources active. Now apply a test source at the output terminals. It can either be a test voltage source VT or a test current source IT. Then calculate the corresponding current or voltage. The Thevenin resistance is VT by IT or test voltage by test current. For example, we can apply VT as 1 volt and find the resulting current IT, or apply IT as 1 amperes and find the resulting voltage VT. Choose whichever makes the nodal or mesh analysis equations easier. We'll solve a complete dependent source problem in a separate video. So that's all for now. I'll see you in the next video.